J that play, like I could be with probability, some probability. So it could be a directed graph.
Okay, we are biased.
And
Yeah,
the orientation is happening.
With the ability and
The line of orientation.
still, I would say it's very artificial. It's not very natural. Because in the real world, it's not that much of a probability. There is a domination of some sort. We also use social media, I guess. I think you can think of it.
Friends.
You need a slightly more structural answer.
And the graph relationship between followers in any app, like Facebook or Instagram.
You think of some like a new technology comes up. What are the rates of adoption? How does the, let's say when, I don't know, how old were you when iPhone came out? I was older. Whenever the new technology comes in, how does adoption happen? Is there some stochasticity there? Good, it's an unknown product. You have to pay real money to buy an unknown product whose utility you don't even know. There's a promise. You really don't know how it's going to perform. You can think of something there.
The number of new users that join is proportional to this.
So it's something very weird. Right? So initially, what would you expect? So let's say as a function of time, what would you expect? For a while, it would be like very small number of people will come. But eventually, this mass will build up. So either the product tanks at this point in time, or it suddenly explodes like what I wanted. So now, what do you think one can build a graph around it? Is there a way to build a graph around it? So you can think of the products as a normal, right? People are joining in some sense that is the mind that product. So initially the probability is some number. You see the graph actually go. Initially it slowly builds up. And thereafter either tanks remains steady or just suddenly explodes. So essentially you can think of it as how people are joining or how is the degree of this node essentially building up. But there are many other products in the market. So it is not a single product. There are so many phones, even when iPhone came out, there are so many other phones. And person is typically going to look for this person. One phone, one of the buy simultaneously all these phones. So there is a certain probability with which he is going to go and associate himself with this product, depending on everything else in the world. Possibly he looks at his other peers, what they are doing. So suppose his friend has bought an iPhone. This guy is more likely to buy an iPhone compared to a peer. You could think of this as one model where random transformation comes into each. So I want you to think, how would you like to think about a random? The biological things definitely will think of. The way virus evolves is nothing but some kind of a random process. So how do influences? I'm just going to take examples after examples from the particular famous thing right now. So how do YouTube influencers get so many subscribers? How does that graph evolve? Or how does the video or audio done by how does it become viral?
It gets shared by people and then again it gets shared.
So, but there are so many videos. Why does very few videos actually become viral? While rest of them equally good ones don't. It's not that the video is something outstanding and that's the only reason it became viral. There's no clear answer to that, but we can hypothesize that possibly a person who has very large and many followers just happen to share it. And that's not going to be a deterministic event. Because the amount of time you see anything is so random that with certain chance a particular person who has so many followers, that also is a random variable. So there are levels and levels of stochasticity here. Of course, each person has a random number of followers. That person has to see that video, has to share that video at a particular time so that it can something happen and it can become viral. So you can, on a space of all videos, you can associate a random graph between videos and let's say people on social media. So think of something from I want you to think about it. Why do we even care about studying something for which you are trying very hard to find very good examples? Abstractness is fine, but there should be some reason to do this.
These graphs are evolving over time, right?
Yeah, you can even forget that it's even extra dimension to it. Even if it's a static thing.
As you have said, it will help us to study the spread of certain virus or things like that.
That is definitely true. But first we should understand what exactly the possible examples of such graphs. I just want you to push yourself. Today's class is not about technical data. I just simply motivate why we study and what we want to study. Suppose you go back and say, call your friends and I'm studying the course on random graphs. Why are you studying them? So you should be able to answer that. So I keep going, but I would definitely prefer that you come up with it. This corridor happens to have a very bad connection for Airtel, at least on this side. You can think of it. So I'll keep going and hoping to get things from you, but at the same time. So why listening? When you think of random graphs having to have anything to do with wireless. So here you are. Here is possibly a base station. There's so many other base stations around the city. And as we're moving around, because of wireless conditions, the probability that you have a stable connection between this base station to you is it should detect this found. So this is the function of the particular location. So it's probability that depends on this probability is little x, little y. Little x on x, y, as well as the distance between x and this. Particular location as well as how far you are. Clear, right? As you walk around, definitely you see those bars going up and down all the time. And that is because of many other things around the world. The Doppler, distance, screening, things around you, and so many other. And now, between each of these base stations, you always have these problems. You can actually listen from a far away base station, just that you're connected to typically the nearest or the best one in terms of this. It's not that your mobile is not capable of receiving signal. It's just that because you have a stronger signal, you just go and register it with this part. So you can equivalently now there's so many other users in so possibly this guy, this guy, and so on. As a so my circles are users and X is our base station. Now clearly you can see the random graph. Also time evolving, but you can forget about that. At any point of time, with certain probability, you have a link between a particular base station and yourself. This is the major source of motivating problems for entrepreneurs. Biology is another. Let's look at. So, I don't know, the motivation of the thing, honestly. What we thought was, so, stones percolate. Or you have a piece of land, water is falling on top of the surface. It eventually, after even at a depth of 100 meters, even further down, water actually gets, we call it, the word is called percolation. How they call it ground. This is the surface and this is water. How does it actually make its way through here? Ground is solid, right? It's not hollow, but somehow water.
That's where stones like that.
No, normal ground, we're talking about normal ground. So water does go through, if you're not concretized, any natural surface, let's say in a jungle, for example, water actually goes through. It's not a porous thing that you would not go down, only the water goes down. So it somehow trickles down by finding certain paths in which you can travel. So what model they came up with was essentially to put this as a square lattice. Go to the fine grained lattice. In each of so either you can do both ways. So either you can say change color here.
Right.
Just
And
okay. So either you can do these vertices as special quantities, or you can take these edges itself as the random quantities. So what they said was that if suppose you're starting from this point, you can find a blue path. All the way to the ground. You're going to percolate. So this water drop is going to start from here, it's going to end up here. And what this blue thing means is that it's open with that is the water can actually go through that edge with a certain property. And another part is closed. Similarly, you can think of this. So this is called edge percolation. This is called bond percolation. So if your neighbor, so water will flow through only if the two neighbors are actually red. Similarly, suppose this is red, this is red, this is red. It's going to follow a path from here. This is called bond percolation.
is this a model they came up to explain this?
To explain natural percolation to large depths, this is the model that came out. This is now from that point onward, it will become classical. You take a random, you take a usual square grid, you can do it in any dimension you like. The results keep becoming more and more interesting as you increase the number of dimensions. Yeah. But 2 dimensions or 3 dimensions is the most first thing you do. And again, you can argue that if there should be some correlation between if this edge is blue, its neighbor is also likely to be blue, but that is more complicated. Initial model is that each of these edges are independently open and closed with probability P or minus P. And under that model, you want to understand can actually the water starting at the top and get to the bottom. So this is another way of taking of the random graph.
One example would be like if there is like a party with 10 people and there is some sort of a way to, I don't know, basically saying how many people do you interact with in that based on people you know.
Correct.
There are a lot of metrics you can consider, but
Yes.
something like
We'll be concrete. So you're at a party, there is people.
there are n people and each person has some set of
Was
There are some friends related to.
as set n by s friends.
Yeah, and there is some chance that I and you will interact. If either I and your friends or I and your some mutual friend.
Right, so exactly, you can do this. So this is I, this is this class of Ni. Now this Ni might contain firstly. Some J also might belong to this.
Hmm.
And then you're associating a probability that I will talk to J. Is that what you see? Okay. So this again is very artificial. You should think of more naturally. So I'll give you wireless network, very natural. This Hammer's-Lewis thing is very natural. You're thinking, they're just everywhere around. So population of a particular species. What do you think is happening there? Or genealogy. So if you pick two random people, what is the probability that they have a common ancestor at a certain level? You think that everybody started from one, that eventually you end up at the top. But so that's why I qualified the question. At a particular level, what is the probability that if you put two humans uniformly randomly, what is the probability that they actually have common ancestor? Is that a random graph? So building on the Zoom, please be vocal, okay?
Graph is fixed, right? You're sampling vertices randomly.
Correct. So that's the randomness. So I can associate a probability between any two people to have a common ancestor at level X, whatever that level might be. Your parents, and so forth. And that probability depends on what level I'm looking at. Also depends on which two individuals I'm looking at. So pairwise is going to be stationary. In some sense, it should not depend on which two people I'm looking at. So this is a special type of graph where the probability with which I put an edge between them is the same for any pair. But if I look closely, how do they look? Then I can do some distinguishing. So you should also think about these nuances. We'll come to this always. That if you look versus you don't look, the probability is completely changed. So if you take a Caucasian person and an African person, what is the probability that they have a common ancestor? Might be different compared to a Caucasian versus a Caucasian. But if I don't reveal anything to you, then they should be the same. So conditionally, everything will change. So lots of places will see knowing little extra makes your job actually harder. If you did not know there's a lot of symmetry, everything can be pushed through. So this is a simple example. Take a relation of humans. Let's call it P or P and G and P is some between P of P. It doesn't depend on which IIJ applicates. It depends on what level applicates. Let me tell you the right story. The faster I go, it's flat. I think it's a tool they want. So as soon as you go fast, it actually launches it off. It's called smoothing. You compare with the limit.
And it's also detecting your hand, right? Should not do that.
Yeah, that I think is a stupid thing. Oh, one more. Just keep quiet until I hear a reasonably motivated example.
Random walk, go to a new city and just walk in random direction.
Yes.
The probability you find a good place to eat.
No, but what is the graph there? You're telling
Roads that they form a network.
yeah, road is a perfectly example of a network. But now what is random? You're
Maybe
moving
I reach
moving randomly.
randomly choose which part to take.
Okay, but what is the random graph associated with this?
At each junction, you have the graph is network, and
Yeah.
at each junction, probability is where you could go.
Yes.
So the question is, what is the walk? What could the walk look like if you follow this probability?
What's the probability you reach a target? Yeah, destination.
But if you knew the destination, then you would walk in a targeted way, right?
But like I said, you're new to the city, you don't.
Yeah, so I understand. I just wanted to be more natural examples.
Passing, if we consider the graph of passing a football between the players in
Why is it random? It's very strategic.
it's, but still means there will be some kind of probability associated
How bad the person is, who can track the ball.
to analyze the player.
So then you should actually do this analysis and trying to figure out who to pass, right?
Yes.
Depending on the distance, how much error you're going to make, how good the quality of the player is, how good a defender is. Too many things. I agree.
There will be many.
But think about something more natural. Give me an example from biology. So here the font is big enough, but I have seen on the video it's very small. So I don't know what is it? You have to fine tune it a little. How do you get it?
You have an ecosystem where you have two similar species, different, who compete for the same resources.
Correct.
If you look at their population over time, no graph.
Think of evolution.
Species graph, genus, all that.
Yeah, let's not worry about technical terms.
Taxonomy.
Yeah, but if you understand what is going on, so there are some random gene flips happening, right?
Mutations.
So how can we associate one graph with that? Is there a way to do that? See, they're all possible combinations. How many? How many billions? You can essentially say each DNA. Like there is some common part and then there is some individualistic part. So let's just look at the common part, which all humans are. See, people can figure out it's DNA human or not. Thereafter, which particular human, that's a difficult story. But there is some common part about human. Now there is some common part about some animals or something. Is there a way to define a random graph on top? You think of whatever.
You can define a function of distance between two different species, so that how similar they are to each other, depending on how similar the DNA
And
is.
now you can say that one particular virus, how likely it is going to infect multiple such species. When the COVID hit, it did not hit other species other than the humans. But there was a possibility people were hiding their lions and tigers and zoos. They were thinking that they will also die, but they did not. So you can equivalently think of a population where, depending on the similarity of the DNA, you can put an edges which are the probability. They will also define what is our effect on external media. But these are very artificially thinking about once. What about internet? What kind of a network is internet? Is there a central entity which is actually building internet?
Internet is more, this was central, it's not clustered. Spread
Right.
out.
So how, like, if you were to model, so suppose your job was to model the internet network, what do you think is a reasonable model for internet? How are people connected to each other?
So peer-to-peer.
Peer-to-peer now. Internet is not peer. If you wanted to communicate from this room to that room, possibly you'll go all the way to the US and come back. For all you know. The traffic might go to the US and come. It's not definitely not peer.
If you were to describe, maybe you'll just describe the connection between main players and your group. Like you make clusters and say how these clusters are connected.
Right. So clustering is an effective way of thinking about it. That what is called as preferential attachment also. That if there are nodes which are in large degree, it's very likely that new person is also going to join them. Once you think of the modern setups, there are existing people. Course, there is existing it is no distribution. You go to a big, let's say, World Trade Fair or whatever, sorry, you see the largest crowd on one side, you're very likely to gravitate towards that. Because there is some bias that if there's so much crowd there, something good must be there sitting there. Similarly, you can think of what is called preferential attachment. The larger the degree you see, you with certain you can normalize it, but the probability of doing and attaching yourself to the larger degree node is higher than the second, higher than the third highest. So that will also give you and this is also going over time. So internet is something similar to this.
So like, if you get a new phone, what are the new apps you will install? Most likely WhatsApp.
Exactly.
Default for it.
Perfect. So you can, on your phone, you can think of each person, what is the number of apps each person has. That will similarly have. It also gets a heavy tail behavior, or what is called as the power law, big component. Okay, so if you had enough, see. What we're going to cover in this class. So I've already put in this slide. What I'm planning to follow. We look at answer with my mind. The number of we said that it has X. Random variable plus equals the distribution data. Now these people will also do the same. Again, it is. Can you keep repeating this process? So this is what is called the branching process. This is how amoeba divides. Or many other organisms which do this self-replicating of some sort. Humans don't do this, but they need two to produce one. But you got model where one is producing more than one. Now, what would you like to study in this one? Think about it. This process is so.
So how many
Each one is doing the same thing at each level.
levels? I mean, maybe it will not, it will diminish, it will finish after the point.
Yeah,
It
so
keep going.
suppose that n is the number of you want to count this probability. Does there exist such that this is an extinction problem. And does this process extend or just keeps going on? This is the problem in this world. Estimating this depending on the distribution of X. That's all. There's no other benefit in this. This is a complete description of the problem we want to study. So appreciate the basicness and how simple it is to state. Right. All I'm doing is I'm just producing progeny IID at every single step. With as many progeny I have, this process is continuing. And all I want to know is, does there exist a level n such that the number of descendants, the number of particles become zero, that is, species has become extinct. It has happened to so many birds, it has happened to dinosaurs. So physically you can think of it. So what do you think would be a random guess to the answer? And when is this greater than zero? Greater than zero?
Look at probability that a single particle has 0 children.
Okay. But that will be a bad estimate. Because once you've grown sufficiently many, conditioned on the fact that suppose at level A, you had ZK number of children, you can say what is going to happen the next. That much I can. Conditioned on that, you can say. But how do you know that one producing zero is not sufficient? Because there are so many of them at level A.
The number of branches.
And we are asking for any n. So n could be at depth, whatever you want. So it's not only that at a particular depth, what is the probability that it will become extinct? Saying, does there exist any finite n at which it will become extinct? So that will be a very crude answer. But think of something very natural without thinking through too much. What would be the guess for this to not happen? Let's say that way. When will it explode? Just think of it.
There are too many branches at the.
Correct, but as a function of the random variable x, which parameter can explain?
Expected number of children.
Okay, how much?
At least one.
Okay,
At least two it will explode. More than one. If it's more than one, it could explode.
can you prove it? That if it is 2, let's suppose the probability is 0.
Okay.
I mean, proof doesn't mean proof. Proof means an idea. Is it obvious that if it is 2, if the expected number of x is 2, is it obvious that that probability is 0? And on the flip side, what it has to be smaller than for it to be non-zero? Can you think of either way? I'm okay with either of them. But 2 is a good number. You should be able to construct at least a hand wavy answer. Why should something like that?
Right. Expected value would be 2 and it could still have non-zero probability of getting extinct.
Yeah, so now why? That's the whole point.
Right. If you have 0 children with probability half and 4 children with probability half, right, then the expected children is 2. But with at least half probability you get extinct in the very first. Okay. So expected number is not a good.
Okay. Anybody else? So we keep hearing this number, right, for humans that if our reproductive levels are 2 per pair, then our population will be stable. If it's higher, it will go up. If it's lower, it will become extinct. So why do you think that 2 is the right number for when two humans have to come together to produce children? That number you keep hearing, right? That all the countries whose population is declining, that number is lower than 2. Places like India, it is higher than 2. Where it still increases. So expected is not bad.
Expected, but it should not vary a lot from that.
No, so once you have the expectation, there's so many distributions have the same expectation.
Yeah.
We're not going to ask which distribution. So the answer is not going to depend on the distribution. That's the main thing. Some moments will be sufficient. So that's why I wanted to think intuitively rather than having any detail that what do you think, let's say the expected value of X should be so that either of the two events happen. If it is less than 1, can you make an argument that then definitely it is greater than 0?
It's less than expected value is less than 1 then with positive probability we have 0 children.
Don't think of one step, think of the whole process. One step you can always compute certain things. The point is that as the tree becomes larger and larger, that's where big things become interesting. In one step you can just compute that. You can just use Markov's inequality and try to say something interesting given whatever is your expected value.
So suppose at a particular level we are having k nodes or like that.
Yeah.
We can expect in the next level to have k less than k nodes. And like that it will be decreasing. Finally, we can expect.
So on average, you're saying the drift is down. Right? Even if it is built up, the drift is essentially going down and eventually it will hit 0. So that's the reasonable logic. Imagine for less than 1. What about greater than 1? The same logic should work. So what is the effective drift? That's essentially what it is. If you're saying for the negative direction, it should work for the positive direction as well. And that's how sharp the answer is going to be. It's in fact, if the expected value is greater than 1, you have one direction, if it is less than 1, you have other direction. At 1 also you get the extinct. So to survive, you actually need greater than. So we'll see this, the first thing we'll do this. So as sharp a result as possible. This is the first thing you'll actually start with. There are so many other models of branching processes. This is the simplest and basic and captures most of the difficulties. Yeah. That only was the first target. Any questions on this? Can you put anything more fancy on your branching process?
Is the maximum What's the max value of ZN?
So if it is surviving, what do you think will happen?
It could either be bounded or it could grow unbounded. Grass.
Okay, so I think what is more likely to happen? It's a good question. But what's the actual, like, suppose you have the regime where it doesn't become extinct. Then I can ask what is the maximum number of progeny at any level I see.
How would it keep increasing?
That's a good question. But does it explode? Does it remain within a boundary? Can I say something interesting about the concentration? Its expectation. You can actually start asking the expected value of the number of particles at level L. That's also a question you should ask. So suppose I give you that information, expected value of Zn. What can you deduce about this probability? So for each n, I give you a number, expected value of Zn. Can you say something about the extinction probability?
And this, if that value is increasing, then probability extension probability 0.
Is it monotone, first of all? Suppose you are in a non-extinct regime. Is the expected value of Zn always going to be at least as large as expected value of Zn minus 1? One would like to show something like this.
Seems it should be a monotone.
So the kind of questions you want to ask are very natural questions. That's why this is very basic thing to begin with. And then when you go to the random graphs, you use some of these results and apply it there. So knowing that if the expected value of the number of progeries you are producing is more than 1 or less than 1 can be used to analyze random graphs. So this is not a random graph. But what is essentially trying to tell you is that what is the degree? So you think of one node degree. What is the degree of this graph in some sense? If the degree is greater than 1, something is happening. Degree is less than 1, something else is happening. So that is how we code this to something more interesting. That will be your first topic of interest, but you won't get to the next slide. You have to build up some probability predictions. So you spend some time getting the right tools and problem. The next and maybe the most important part of this course. Plus model of an animal. So take n of it. Pick any two of them and put in vertices. And then be independent of everything else. The simplest graph. Take any nodes. Pick any pair. Max them in an S. Then it's also called G. And let it remember that. So now what kind of questions would I ask? This is a complete description of the graph.
Connectivity.
Okay, define connectivity.
Number of connected components.
Define the number of connected components.
Connected component. Two vertices are in the same connected component. One is reachable.
Right. So connected component of vertex I is the set of all vertices J particular. J. So that's my connected component of I. All the vertices that I can reach from I. So now I have the definition of connected component of I. What would you like to ask? How big is C of I? Is that a reasonable question to ask? See, C of I doesn't depend on I's identity. So the distribution of Ci is the same as distribution of Cj. That one is clear. Is that clear? I'm doing nothing special about a particular vertex. Without looking at the vertices, I made these edges. So whichever node I pick, see if I look inside the graph, is J connected to more than 10 people? And then ask for this question, that answer might be very different. Currently, I'm just taking any vertex and asking what is the size or what is the connected component of Ci. So the distribution of Ci should not depend on I. Because I've done nothing special with respect to I and J. But if I were to ask you what is the connected component of a vertex I, which has degree greater than 10, and then I ask you some other degree 20, those two distributions are going to be completely different. So this is a reasonable question to ask, right? What is the size of X vertex? Yeah, I don't have to qualify CFI, so I can simply drop this I as well. Any X. Total expected value as a function of N and P. What do you expect to happen?
Small values of P, it might be close to 0 or 1.
See, at least NP, right? There can't be smaller than NP.
Okay, what is the function?
See, it is strictly greater than equal to NP. Because you are always connected to, on average, directly connected to. It's just that from here, how are you going to pass the remove pass of the conflict? So this is definitely greater than times. That is your own neighbors. So the most interesting question one wants to ask is what is the value of P such that the expected value of the connected component is order n. That's the first question you ask. Look at the importance of the question. That the connected component is the same order as the total number of vertices. What is the value of P for which that is true?
Overall, it's always order n.
Sorry.
Isn't it always order n?
No, if I make P equal to 1 by n.
Oh, okay. Thinking P constant.
No, then it's trivial. So I have a control of P with respect to n. So for example, if P is 1 by n, this number is simply 1. But the answer will turn out that that is sufficient to make the connected component equal to order n. So that's why these things are interesting. So I should really say P sub n if I were to. So GNP essentially means that n vertices, n is large and P can depend on n. That's what essentially means. If P is constant, this graph is not interesting. Then almost all the questions you have are kind of trivial. So what you want to really find is what is the smallest value of P that can depend on n, such that such and such properties are actually true. So one property is that I want the connected component to be roughly of the same size as the number of vertices. What other question can you ask? You know, what is the diameter? Everybody understands diameter of the graph. Maximum number of hops you need to go from any node to any node.
1 second.
1 second, yeah. So diameter is nothing but the maximum number of hops you need to go from.
Maximum distance between two words.
So suppose this is x and this is y, and there is a edge connecting these two. So I can go into hops from x, let's say z, and z to y. See, if I put distance here, then it will be sum of the distances. So currently, we should think of all of this as edge weight is 1. So the total length of the path you have to go from x to y is its diameter. For a particular x and y pair, diameter for the graph is the maximum of all possible xy pairs.
Okay.
We can equivalently ask what is the diameter of this graph. What do you think of that? For P close to 1 by n. Again, otherwise you can say that stuff like this. Okay.
May not even be connected, right? Then how do you define diameter?
Yeah, so it's part of the problem. When I'm saying diameter, it better be connected. So with high probability, you first need connectivity, and then only you can talk about the number of hops to get there. Will turn out the diameter is just 2. No. Incredible. It's completely counterintuitive. Once you have connectivity, the diameter is just 2. These graphs are actually simple to describe, but the results are pretty surprising. This is also a phase transition. The first place where you hear about phase transition. If you go to the physics class, you hear about this word, phase transition. Essentially, what it means is Pn larger than 1/n something happens. Pn smaller than 1/n something completely opposite happens. And at criticality, which is exactly at 1/n, either of the difference. That is what is called phase transition. That suddenly something just changes. And you also always want to find a critical mass. So in this case, it has happened 1/n, where having a connected component on the same size and the same order as the number of vertices, then suddenly it will drop to little over. As soon as you go slightly better. And something very similar to connectivity as well as that.
So is it like when it's less than 1/n, there are very small components after this?
Suddenly, and very, I think you're already there. If you have a giant component, like that is what is called, that one big component is called a giant component. It's only one. The giant component is unique. Once you have a giant component, essentially all these small clusters suddenly have connections between them, each of them. So you can't have n/4 nodes here and n/4 nodes here connected within each other, but having no connection between them. All those results need to be real, but that's what happens. So most often in most of these models, whenever you have a giant component, you're typically able to show that it's also unique. It cannot be that two giant components exist simultaneously. Once you are big enough, you just assimilate it. That's what it is. So that's a Australian graph. There are many variations to this. I don't think you have time to look at that. Move on to what is called as a random walk. This might actually think of it, discrete time approach. So what do we do? Start at location 0. There are many ways to display this. This is my pattern. I go +1 at each step I do this without worrying where I am. This is the simplest model of a random. Like you describe it, you're walking around the city, at each corner, you just pick any of the 4, forgetting where you came from, any of the 4 directions. It's doing something similar. It's forgetting how to write whatever locations. It goes, takes one step ahead, with probability half. One step behind, with probability half. Now, what kind of question would you like to ask?
Expected position
After?
and
Okay. So let's go on this. Let's start with it. This one.
no, there.
Yeah, this one.
So it is
Right. This is the way to write this. Inside this plus minus and increment. What do you want to find? Expected value is there. That is very easy. So if you write in the correct form, some questions will be trivial. But what is the more important question you should ask?
Will it ever come back to zero? When what's the chance it will?
Okay, that's a good question. So what's the problem question?
How many steps to come back to zero? Maybe expected.
Yeah, expected time to come back to zero. Okay. What do you think will it look like? You can think of this as just a Markov chain with up transition half and down transition half. So it's in your language, it's a null recurrent Markov chain. If you know what to null recurrent, possible recurrent, and transition. You already know the answer. It's a null recurrent discrete time Markov chain. So it keeps coming back, but the expected time is. So that's what null recurrence means. It's a null recurrent chain. What it essentially means is the positive drift and negative drifts are identical. If it's one drifted in one direction, then certain things happen.
Yeah.
But here, what you're going to see is that it does come back to zero infinitely often with probability 1, but it takes long enough time to come back. Okay, what I thought you would jump at something which you already know.
I have not worked with Markov chains.
No, not even Markov chain. Don't have to worry. You know central limit there.
Some clear caution.
Yeah, exactly. If you take sufficiently many random variables, add them up, and normalize them. The normalization is the trick. If you normalize with 1 by n, it's close to the expected value. If you normalize by 1 by square root n, then it is close to the Gaussian. Now, can you tell me what is happening here? So essentially, if you plot it, it's not going to go beyond square root n in some sense. So Zn by square root n is roughly Gaussian. So that will jump at it. So if you were to simulate this, you will essentially see that around zero, with whatever standard deviation it is going to keep wandering around, keep coming back. Very few times it goes beyond that. So that is just
one fraction of the time it is that question.
You can deduce something from there, but the simplest spread is easy to find because of the central limit. Because these xi are IID, you just normalize by square root n. So roughly it's looking like square root n. The expected value of Zn is 0. So that is clear. But the distribution is roughly, we should think of it as behaving like in n steps, its spread is spreading as square root n. So some of the interesting questions people ask is, what is the expected time to cross a particular level? So suppose I fix 10,000. What is the probability that in so many steps I am crossing 10,000? Because there's so many ways in which I can do it. I can either go always to the right, keep going back, keep going back, keep going back. So very simple process, but again, very interesting answers you can have, very interesting questions you can pose for it. Any other questions? Gambler's ruin is sitting there. So if you go to a fair casino, you're starting with whatever prize money. What is the expected time to hit zero? Because they don't let you play with credit. So you'll have a wall at zero. That's it. That's the only difference.
Mhm.
If you're playing a simple tossing game with your friend, how long before you actually run out of that? It's a famous chemist for me, you can answer. I'll encourage you to, we'll come to this few months down the line, so I'll encourage you to just think about it. What do you expect? How long will it be? Or you can even say, what is the expected winning I'm going to make? So if I start with a certain amount of money, so how far to the right you're starting? It will depend on that.
So if I win, they get one.
Yeah, so you just play a tossing game. Every time you win, you get +1. Every time you lose, you get -1.
Mhm.
So money is not important. You're just starting place is what I'm counting. So eventually you hit 0. So this will be our transition point to percolation. Let's just say edge percolation. Each edge open. And then suppose it's the origin. Okay, everything is translation is very. I don't have to worry about where I'm starting. I can say.
Excuse me.
Question?
Yeah,
Yeah, go ahead.
yeah. So, respect to the random question thing that we are discussing. One interesting thing that I was thinking about is what is the number of ways in which the particle can come back to zero after exactly n steps?
Yeah,
I believe it to be the nth Catalan number.
could be. I don't recollect that.
Okay.
Catalan numbers typically have this two-dimensional version, I remember. So if you draw a two-dimensional grid, let me use this example anyway I have on the board. So suppose I want to start from here and reach a point n, n. And I can only go to the right or up.
Yeah, that is exactly equal to the number of like a Catalan number. Yeah.
Correct. So that much I know, but I don't know in what dimensions.
That is not Catalan. Catalan is like if you have the x-axis, then you can never go below the x-axis. So you're allowed to go.
You're allowed to go down as well.
So the moment says up right
Yeah.
and up down.
Both
Sorry,
are
right down.
Okay.
So the movement is always diagonal to the right.
So this might be half of it. I don't know.
This is not Catalan.
But on the one-dimensional line, I don't remember if there is any connection to Catalan. What he's asking is the Marco chain I drew, the number of ways in which I come back to zero in n steps. Does it have any connection to this? So I'll reserve this answer. Simple answer is currently I don't know. It could be true. I don't see it, but
Going horizontal is +1 and going up vertically is -1.
Yeah, exactly. That's what.
If you reach n, that means you reach 0.
Yeah, that's the argument which I was also thinking.
yeah, it could be done. This has to be appropriately defined because -1, what is -1?
Vertical, going up.
Going up, but here you're staying in the same place.
So we're counting the number of paths from the origin to n, n. Every time you go right, you
Right.
+1, and every time you go up, you -1.
Okay. So I agree. So just on the straight on that line you're saying, so the difference is 0. You're right. This is also used. This tree is also used to say something about a random walk on 2D doesn't come back to 0. On 1D, it's all things are okay. In multiple dimensions, they just go far away. Okay, so coming back to percolation, what I want to ask is the connected component of 0. When is this unbounded? So now there's no n. It's just a two-dimensional grid. So what is the probability that this is greater than 0? I want to find the minimum P. Is the question well defined? That I want the smallest P for which my connected component to have unbounded large size, that probability should be greater than 0.
It's an infinite grid.
It's a good, very good. So there is no n. And typically you can ask, again, there will be a case transition. And surprisingly, the answer is exactly 1/2. Precisely 1/2. So that will not cover. It's too complicated approach to get to 1/2. You give an upper bound and give a lower bound, which will sandwich 1/2. So you should try to see, can you at least prove that P is greater than 3 volts? This is greater than 0. And P is less than 1/3. It is 0. These two are not too difficult. You start thinking about it right. To exactly get to half, that took many years for people and it's very complicated. Not something you can cover in course. The precise answer is 1/2. Sharp. Okay, so now we build upon the strict grid percolation. It's called random. Moment I'm not going to factor the moment was on point process. Think of 1 by 1 square. Total points from the end. Now, this is my point. XT point. So this is our points. And draw these circles around with radii r around each other. R is fixed quantity. And I will draw an edge between these two axes if these circles over. Then the distance between two is at most 1. You can do it with R itself. I'm just doing it with 2. So now there is randomness in terms of the location. So it is called random geometric graph rather than a grid graph. It's not directly, you cannot map it to a grid graph. The clear what is going on? Just putting these endpoints uniformly randomly and connecting any 2 points which are at distance of 2r from each other. That's what it is. Now again I can answer this. Now there is n here. You simply extend this to all of R2, but for the moment I want to ask what is the probability that connected component of there are also boundary effects. So ignoring those, what is the probability that the connected component of let's say point located at 0 is now we can ask for R. What is the minimum R for which this happens? N is fixed, R can depend on N. It's also called Gilbert's Fitts model. Now we're going to closer to wireless application. You should really think of two wireless nodes can talk to each other if they're at a distance of R from each other. That's what essentially is going on. So now we can think of a wireless network that if I have a source here, if I have a destination here, how large should I keep this radio range such that I can reach S to D wherever it is where it is. We have not studied this way, but this is how the networking of the communication cover got it. And that actually 20 years ago, somebody wrote a very influential paper in information theory called capacity of wireless network. So that not only started wireless people to think about it, but information theorists to think about it. They probably started thinking going back. So there's a probabilist in ISI Delhi named Rahul Roy. So getting recorded, so I have to be very careful. So at least he told me himself that he had written a book called Continuum Percolation before this paper appeared. So typically when you write a book, it says zoom and then suddenly just keep going down all the time. He saw the double dip or the second peak right after this paper came out. So not only that the interest came back from wireless connectivity, but actually the probably started looking by it. So this model is like the starting point of that. You can do many other fancy things on top. So this will be more or less then we will get into the wireless world. So we need to run a little more complicated graph on top of this. So there is something I have looked at in detail. Can you see this? This coordinate. This again. Think about 10 units square. This is very specific to wireless world. This is mine. That one. This is mine. What happens? Transmitter is trying to transmit information to receiver one. At the same time, transmitter 2 is transmitting information to receiver. Now, because these are not wired connections, you also see interference. This is your phone is trying to overcome it all the time. There are signal processing algorithms running on your phone to make sure that this is not a mess. What happens is, let's call this the power of intended signal. That's P and power of the interference. As I. So the model is that communication is successful if P over I plus or thermal noise, which is always present, certain variance, 3 marks. You don't know this, you can take 0. But everything in this world, any circuit you run, there is always thermal noise. So that's what this is. If it is greater than the threshold for a data, then communication can happen through these nodes. So equivalently, an edge exists in our language. If this condition, this is super complicated condition. Just think about it. Everything else we have done so far has been local. This is the first place where the existence of an edge depends on the full network. Because this I is coming from every possible node in the network. So there could be as many as networks. So node here, which is P3, P4, all of them contribute because this I is nothing but the summation of all the interference. So there is a really intended transmission happening here. Under interference of all possible transmissions that are happening around the network. So this quantity is a completely global quantity. It's a random graph, but there is no locality at all. If something happens far away in the network, it controls the performance of your network. Does it exist or doesn't exist? This is what is called a signal to interference plus noise ratio graph. So the numerator is signal power, the denominator is interference plus noise. So this is again a very interesting graph studied in great detail by now.
So is this static or is it also considered movement?
For the moment, you can think of static, but what you really, not just the dynamicism in terms of time changing, what you can do is as a network controller, you can decide who should transmit at the same time. So even if it's a static graph, you can call this particular base station not to transmit at this particular time so that everybody else in the network can get through their packets through and then ask them to come back again and transmit. So there is an aspect of scheduling on top which can completely control the performance. But for the moment, they just think of it as a static graph. You can silence somebody and improve somebody else's day. That's amazing.
Power will depend on distance, right?
Power will depend on distance, also local conditions, like you're standing next to a tree, you're inside the basement, so all that is called as fading. But definitely distance, and distance is exponential. So d to the power minus alpha is typically what you get, where alpha is greater than 2. So that is just physics.
It will be quadratic,
Yeah, it's called negative quadratic.
1 by r square.
1 by r squared or more. You might have seen this in 12th, 11th standard or standard.
So how is it
Now
exponential?
electromagnetic waves. So the exponential d to the minus of distance is d. E is proportional to d to the minus. It's power law. All right, any questions? That's pretty much I wanted to cover today. Well, nothing. Good. If any of you looked at the flyer, this is the advanced flyer. It was color. I don't think I will conduct any final exam. So it'll be homeworks. And essentially, I want to do a project, but depending on the number of people, you can decide what to do. You can substitute for a paper presentation. Just to a project. But you should quickly decide when you want to grade the course, because that will determine how the class is going to progress. Any questions? Any questions from the Zoom class? So on my TV, when I'm writing, the font is large enough. Are you able to see sufficiently reasonable font?
Yes, yes.
Okay. Any questions?
Yeah, can you please explain this SINR graph because I could not understand anything.
Okay. Let's think of 10 people. Row. 2 people are sitting on this corner, 2 people are sitting in this corner, somebody is here. And they're all talking at the same time. Forget about the text. Now, what do you think is the quality of this link if all of them are speaking at the same time compared to when all of these guys are silent? You're going to have a better quality conversation. So let's think of this power between these two guys' speed and the interference they cause at the receiver to be high. Now the question is, how is P and I related to my quality? So one way to do it is just to take P over I. So as long as P divided by I is large enough, I'm able to have a conversation even in the presence of those guys. If I is 0, great. But if I is not 0, but still it's not too large, I'm still fine. So forget the wireless nature of it. That's pretty much. Is it clear now?
Yeah, it's clear.
Okay.
What is the randomness?
Randomness is location of the people. So the speed will depend on the distance between them. And how far is your next people from. Okay. So no questions, class is over.